Okay, so now f sub x is this 10, f sub y, now we consider f sub y, its partial derivative by y, then mu xg as constant. So first term mu xg as constant, y is derivative 1. So first term is x times g. Second term, x is constant, keep it. Natural log y is derivative is 1 over y. So it's subtract x times 1 over y, is 1. And the plus y times natural log x is derivative. So natural log x is constant, keep it. Y is derivative 1. 1 times natural log x, so it's natural log x. This one. It's this one. This one. Okay, I write down here. It's yg subtract natural log y. And the xg subtract this one is x over y plus natural log x. This one. And the f sub g now variable is g. I mean, consider partial derivative by g. Then mu s and y is constant. So s and y are constant, keep them, and the g is derivative 1. So it's xy times 1. So it's xy. And s and y is constant, so they are constant. It's derivative 0. And they are constant, it's derivative 0. So just have this term, this one. Just have this term, this one. Okay, and the gradient f is this one, and we want to know gradient f of 113. So gradient f of 113, we could solve it now. Gradient f of 113, just plug in the value 113. So now it's 1 times 3 is 3 subtract natural log of 1. 3 subtract natural log of 1 is 0, so just 3. And here is 1 times 3, so it's 3 subtract x over y, so it's 1 over 1, so it's 1. Plus natural log of 1. Natural log of 1 is 0, so this one. Here, note, natural log of 1 is 0. We know that natural log of 1 is 0. And x times y is 1 times 1, so it's 1. So now it's 3, 2, 1. So the vector is 3, 2, 1. Yeah, the vector, let me see. 3, sorry, is something wrong, right? X, here we still have 110, sorry. We still have 110. Yeah, I have not done it. So for the first derivative, for the partial derivative by x, the first term is yg, second term is this one. And the last term is derivative, y is constant kb. Natural log s is derivative 1 over s. So we should plus y times 1 over s, y over x, this one. We still have this term. So this one we still have this term. I mean, 1, here is 3 subtract natural log of 1 is 0, but we should plus 1. And here is 3 subtract 1 plus 0. And here is 1, this one. So it's 2 is 4. So the vector gradient is 4 to 1. The gradient is 4 to 1. So as you see, we have not considered this one, P and Q. I mean, the direction U. We haven't talked about U. Then for its gradient, it's already fixed. For the gradient, it's already fixed. Okay? So if I give you a function f, and I give you a point P, then actually for its gradient, at this point, for its gradient, it's already fixed. Actually for the gradient is a gradient vector. A gradient vector is a vector in R3. So for the gradient vector, it's already fixed. Once we fix the point, it's already fixed. Okay, and then now we should decide the direction u, but it should be univector. So now the direction is that we have the point P, and from the point P to the point Q. So to the point Q. So the direction is this direction, PQ, right? So the direction is PQ arrow. So PQ arrow is the point Q subtract the point P. So it's the point Q subtract the point P. So it's 2 subtract 1, 3 subtract 1, 1 subtract 3. So it's 1, 2, negative 2. This one. But this vector is easy to see. I mean, its length is now 1. It's not univector. So we should divide by its length to let it be univector. So you should consider its length. Then its length is square root of 1 square plus 2 square plus negative 2 is square. Its length is this one. Its length is this one. So it's equal to square root of 1 plus 4 plus 4. So 1 plus 4 plus 4 is 9. So 9 square root is 3. 9 square root is 3. So now the unit vector u is pq over its length. Divided by its length. So this vector divided by its length is 1 over 3, 2 over 3, negative 2 over 3. This vector u. Okay, so once we have the vector unit vector u, and then we have a gradient vector. So the result is duf of 113 is exactly gradient and the unit vector their gradient f of 113 and the unit vector u their inner product. So their inner product, just consider the inner product. So each term there's product. So 4 times 1 over 3, so it's 4 over 3, plus 2 times 2 over 3, so it's 4 over 3, plus 1 times negative 2 over 3, so subtract 2 over 3 is what? Subtract 2 over 3. So it becomes 4 plus 4, 8, subtract 2 is 6, so it's 6 over 3, so it's 2. So it's 2. So for the first question it's 2. So for the first sub question is 2. And how about second one? For second one, we want to find maximum rate of change. It also means maximum directional derivative of f at this point. And what's the direction it should be when it has the maximum rate of change. And when it has the maximum rate of change, what's the direction? Okay. So now, as we say, once I give you a point and give you a function, and its gradient vector is fixed. And now, here we have a gradient vector. It's fixed. Gradient vector is fixed. Gradient f113 is fixed. And now we consider the direction. U, it could be here or it could be here. We don't know. Yeah, just one direction. So now, what's the directional derivative? Directional derivative for our formula, directional derivative is exactly equal to gradient f113 and the unit vector their inner product. But as we say, two vectors their inner product is equal to, we have the formula, if the angle is theta, then we know that cosine theta equals gradient f is length times unit vector is length. And numerator is gradient f and the unit vector their inner product. Right? Their inner product. Or you could see gradient f u their inner product. This one. So for their inner product is equal to cosine theta times their length, the product of their length. So it's equal to cosine theta times each of their lengths. Unit vector times cosine theta. This one. But here, although we don't know the direction vector u, but it's unit vector, so its length must be 1. Okay, although we don't know which direction u, but its unit vector, its length must be 1. So for each direction, its directional derivative must be equal to length of gradient multiplied by cosine theta. So what's the maximum about this value? The maximum, it must be let it be 1. Then it has the maximum, this value is our maximum. Right? It's our maximum, and it happens in this case when cosine theta equals 1. But when do we have cosine theta equals 1? Cosine theta is of the form. So cosine theta equals 1 is exactly in the case when theta equals 0. So it means that the angle between these two vectors is 0. It means that the unit vector we choose is exactly in the same direction. as gradient f. So unit vector u we choose is parallel, not just parallel. It's in the same direction. It's in the same direction. Gradient f is in this direction. Is in this direction, and it has the maximum value. This guy. Gradient f is length. Gradient f is length. Okay, so it's the detail about the result. So I just explain it again. So, but for this one, of course, you could write down the solution directly. But you should write down. I mean, you of course, you could write it down directly. I mean, since we know that gradient f, this one, 113. Since we know that is equal to 421, so directional derivative f 113, it has the maximum. It has the maximum. It has the maximum. Its maximum is gradient f is length. Its maximum is gradient f is length. So it's equal to square root of 4 squared plus 2 squared plus 1 squared. So it's square root of 16 plus 4 plus 1. So it's square root of 21. And in which direction? In the direction. So in the direction to the same direction gradient as gradient. The same direction as gradient. So in the direction gradient f 113. So direction gradient of 113 is exactly 421. 421 in the same direction. In the same direction. So it's the solution about second problem. Second subproblem. Second subproblem. So the value, maximum value. So maximum value is this one. So maximum value is square root of 21. The direction is this one. Okay. Yeah, so now let's see the last example. The last one question. Yeah, directional derivative is actually is one of the most important thing. Yeah, it's very important. It's the most important thing in chapter 11. You should know how to find its rate of change. And the maximum rate of change. Yeah. Okay, so now let's see the last one example. Normal tangent plane and normal line. Find equations of tangent plane. But as you see, of course you should know the formula to consider the tangent plane and normal line. But before that, you should consider partial derivative. And when you consider partial derivative, you should change each one in their derivative formula. Tangent plane and the normal line. To the surface. The surface satisfies this one. Cosine xyg equals xy squared plus dq subtract exponential x squared g at a point 1 negative square root of 2 0 at this point. Okay. So now let's see. Okay. So now let's see how to solve it. So we just follow the formula, but follow our result. But in our result, we should have a label. We should have a capital function, and if xy satisfies this equation, once we plug in the capital function, you will get it's a constant. Then we could consider its label surface. We could use our formula. Just consider its gradient. So now we should consider capital F of xyg. and defined by their subtraction, right? So we could define by their subtraction. Cosine xyg subtract xy squared subtract g squared d cubed subtract negative, so it's positive exponential x squared g, this one. And if xyg satisfy this equation, then you will see f of xyg equals 0. F of xyg equals 0. Right? So it's a constant, so as we say in class, but actually for the process is relative to the material in section 11.5. It's about the implicit differentiation, and we also use chain rule to explain it. So probably it's a little complicated. Anyway, so for this result, which you can see is gradient vector. Gradient vector is the normal line of for the tangent line it has normal vector, and for its normal vector is exactly the gradient vector. Okay, for this function, its gradient vector is exactly the normal vector of this tangent plane. Okay, for this tangent plane. Okay, so gradient vector, so we should consider gradient capital gradient f. So gradient f, you should consider fx, fy, fg. This one. So first one. So now it's inside, it's outside. So cosine function is its outside function is derivative is negative sign, and inside we should keep it. But first one, the derivative is x, so yg is constant, keep it. So its derivative is 1 times yg, so just yg for the first term. And second term, derivative by x, differentiated by x, so y squared is constant, keep it. So y squared times 1, so it's subtract y squared. And now it's and now the variable is x, so it's constant, so its derivative is 0. This one, its derivative is itself. But inside we should multiply inside function is derivative. So its derivative, consider its derivative. So now g is constant, keep it. X squared is derivative 2xg. So this 10 for the first one. And the second one, f partial and partial y, then first it's inside, it's outside. So for the outside function, we always have this 10, negative sign xyg. But inside function is derivative, now variable is y, so it becomes x times g for the first term. And second term, y is the variable, so mu xg as constant, so it's constant. Y squared is its derivative is 2y, so subtract 2y times x, so 2xy. And g is constant. If we consider its derivative by y, then constant is derivative 0. And this term, x squared g is also constant, its derivative 0. So we just have these two terms. And fg, so the first one is the same, negative sign xyg. Multiplied by inside function is derivative, but now variable is g, so xy are constant, keep them, and g is derivative 1, so times xy. And xy are constant, so its derivative is 0. If we consider the variable we differentiate by g, then xy squared is constant, so its derivative is 0. And this part is not subtract 3g squared. And this part is plus exponential x squared g. But inside function is derivative. Now x squared is constant, keep it. G is derivative 1, so it's x squared. It's 10. So we have this one. And once we have this one, we could write down its gradient. Gradient f. The point is 1 negative square root of 2, 0. And the first one, just plug in the value 1 negative square root of 2, 0. But when you plug in the value, actually you could see there is some trick. It's our x value, y value, g value. So for g value is 0. So once you plug in this one, you have the value 0. So it's 0, it's 0, it's 0. And sine 0 is 0. So this 10 is 0. This 10 is 0. This 10 is 0. Actually, for this 10, there are zeros. And the g equals 0, so for this 10, it's 0. Right? and for this 10 it's also 0. It's also 0. Okay, and this 10 is exponential 0. Exponential 0 is 1. Exponential 0 is 1. Okay, so there are some, so actually you could cancel some of them. It's not very complicated. It's just it seems that it's complicated, but actually once you plug in the value, it's not complicated. Okay, so the first 10 is subtract negative square root of 2 is square. Square is 2, so negative 2 plus is 0, so just this one. Second one, negative 0 subtract 2 times 1 times negative square root of 2, so it's negative, subtract negative plus 2 times square root of 2, 2 square root 2. And the last one, 0, 0, 0, 1 times x squared, so it's 1. It's 1. So it's the vector. It's the vector. It's the vector. So gradient in this one, then we could decide the tangent plane, normal line. Write down the solution directly. Actually, write down the solution directly. If we say tangent plane is normal vector is exactly this one. Tangent plane is normal vector is exactly this one. Then we know it's negative 2, 2 square root of 2, 1, and the inside, and each one we consider the point. Our formula in section 10.5. Here, for this plane, it passes through this point. It passes through this point. So you should consider x subtract 1, y subtract negative square root of 2, so it's y plus square root of 2, g subtract 0 is equal to 0. As we say, it's a plane, and for this plane, it passes through 1 negative square root of 2, 0. It passes through this point, and its normal vector is negative 2 times square root of 2, 1. This vector is the normal vector. If it's a plane, then the coefficient means the normal vector. It's the normal vector actually. For this plane, it's the normal vector of the plane S. Okay. Now how about normal line? Normal line, it has the direction and normal vector. So it's negative 2 symmetry equation. Symmetry equation in the denominator is the vector negative 2 times square root of 2, 1. And the numerator just put down this one. Since it passed through this point, so let's subtract 1, y subtract negative 2, so y plus square root of 2, y subtract negative square root of 2, so y plus square root of 2, g subtract 0, then we are done. Here is the tangent plane, here is the normal line, and we are done. Okay, it's all.